Okay, so we want to have a look here. Oops. We want to show that this series here from 1 to infinity sine n over n converges. So what you have to do is say that this is equal to 1 over n from 1 to infinity times sine n here. And you can use Dirichlet's conditions. It says this will converge and then you call this an and you call this bn, will converge if number one, an is null, and here it's true because as n goes to infinity 1 over n goes to 0. 2, an is monotonic, and this is true because clearly 1 over n plus 1 is smaller than 1 over n. And 3, the sum of the bn is absolute. The absolute size of the sum of bn all the way up to infinity, that has to be bounded. So these two are obviously true. We only have to check the last condition. So let's calculate here the sum from 1 to k of sine n. That's equal here, absolute value, 1 to k, and then we can use an identity here on sine n. We can say that's e in minus e minus in over 2I. That's a complex an identity from chapter on complex numbers. So each of these guys are actually geometric, but what I can do is I'll just take the 1 over 2I out, and then it's the first one minus 1 over 2I, and then the second one. So the first one using the geometric series sum formula, because it's going EI, E2I, E3I, and so on, and that would be EI over 1 minus E minus IK over, plus, over 1 minus EI, and then this one here would be E minus I, 1 minus E minus IK over 1 minus E minus I, using the SN formula for a geometric progression. Okay, so for complex numbers this will be less than or equal to the absolutes of 1 over 2I times the absolute of EI times the absolute of 1 minus E IK over the absolute of 1 minus EI plus the absolute plus 1 absolute of 1 over 2I, then absolute of E minus I, then absolute of 1 minus E minus IK, and then all over absolute of 1 minus E minus I. Now I need to get a formula for all these 1 minus EI terms. I'll just do it on the side here. Okay, so just note that the absolute of 1 minus EI theta, That's the absolute of 1 minus cos theta minus I sine theta, which is the absolute of 1 minus cos theta minus I sine theta, which is the square root of 1 minus cos theta squared plus sine squared theta, which is the square root of 1 minus 2 cos theta plus cos squared theta plus sine squared theta, which is the square root, that's a 1 and that's a 1, that's a 2, minus 2 cos theta. Is that right? Yeah. So we can see that this is less than at most root 4, which is 2. So we have an upper estimate here. But my theta could be k. And that's a this doesn't really have a minimum value, does it? Oh, but I don't have to worry about it having a minimum because in the denominators the theta is 1 here. So what I can do is just say that this is 1 over 2. This is 1 over 2. That's 1. That's at most 2. And then the same thing here, 1 over 2, 1, at most 2. And each of these will be over this here when theta is 1. So that's 2 minus 2. Actually, there's the common denominator, so why don't I just put it all over that? Root 2, 1 minus cos 1. So that's the bounds. Actually, that cancels that, that cancels that. So I can clean this up a bit more. That's 2. And 2 over root 2. So that's root 2 over 1 minus cos 1. And that's the bounds. So we've shown that it's bounded, which was the last requirement there. Let's see. 2 over 1 minus cos 1. Let's have a quick calculation of that. 2 square root 2 over 1 minus cos 1. That's 3.07. So we're basically saying that this should be less than or equal to roughly 3. Now that's an overestimate, because when I was looking at what type of values you get here for different values of k, it always seemed to be roughly less than 2. So I mean, I've overestimated the bounds here, but that doesn't matter. It's less than or equal to roughly 3 point. Well, actually, I'm permitted to increase this, so I want to make it neater, or not neater, but I could give it a numerical value that's clear to see. I'm saying that this sum here is less than or equal to, well, it won't even be equal to, I know that, be less than 3.1. So it'll never exceed or even reach 3.1, so it's clearly bounded.